Alright, hello everyone. So we're going to continue our discussion with capacitors. So we talk about the capacitor equation, simple capacitor equation, Q equals CV. We talk about um, how to find the capacitance of a parallel plate capacitor, which is the capacity equals epsilon naught A over D, area divided by the plate separation. We also talk about series and parallel arrangements. If we have multiple capacitors, how to find the total capacity of those in series and parallel. So today we're going to discuss another aspect, electrical energy storage. Capacitor can store energy. So let's say we have a parallel plate capacitor, you connect this to a battery. Capacity C, voltage is V. Now, when you connect this empty capacitor, let's say initially it didn't have any charges in it. Now the battery is going to move electrons, charges into the capacitor, and the capacitor will get charged. And it will accumulate amount of Q, charge Q on the capacitor. And that Q is given by Q equals CV. The voltage of the capacitor, when you connect it, the voltage going to increase in the capacitor, right? It charges up to the point where the voltage of the capacitor becomes the battery voltage. So if it is a single capacitor connected, all that V will eventually appear here. So the voltage of the capacitor also becomes V. If you have multiple capacitors in series, that will be different. Remember, we talk about this. The sum of the voltages, the summation becomes battery voltage. But if it is just one battery, the entire battery voltage will eventually appear across the capacitor, and then we say that it's fully charged. It will stop accumulating further charges. So at that point, we have a charged capacitor. Now if you remove it from the battery, what we have is this, a charged capacitor, total charge of Q with a voltage V across it. Now this thing itself acts like a battery, like an energy, like a voltage source. And then we can use this in place of a battery. For an example, if you connect this to a light bulb, it's going to discharge through the light bulb. So this energy stored in the capacitor will come out as light, right? So it's an energy storage device, means like a battery, it has the energy to move charges, it has energy to move electrons, create current. Okay, so give me 1 second here. So it's a storage device, so it has the ability to move electrons, move charges, produce current. Now energy stored in the capacitor is given by these equations. As shown in the PowerPoint slide to the right, we can say energy, if you connect the capacitor, like this diagram 1, to a voltage of V and a capacitor of C, the energy stored is given by half Q squared over C, also equals to half CV squared, also equals to half QV, right? So what are these equations? They all says the same thing. It's good if you can remember all of them, but even if you remember one of them, that's still good enough. So for an example, let's say U equals half QV. The charge, the energy stored in the capacitor is given by this. Now if you want to go from these to the others, you simply have to replace one term. So for an example, half times, instead of Q, I have this, right? Q equals CV. I'm going to use this and replace this Q using that half times CV times V. So it gives me half CV squared. It gives me the second equation. Now start here again, half QV. Now I'm going to rearrange this. I'm going to replace V with this equation. So I have Q equals CV, the basic capacitor equation. This tells me Q over C equals V. So I'm going to take this and put it over here. So that gives me energy equals half times Q over C, gives me half Q squared over C. So these are like different forms of the same equation. All you need to do is remember at least one of them. My personal preference is energy equals half CV squared. You know, this has the same format like the kinetic energy, like half mv squared, so it's kind of easy to remember. You just replace capacity, and of course this is not velocity, it's the voltage. So here's the equation to find the energy stored in the capacitor. Okay, let's move on and let's work on a couple of examples. All right. Okay, so here you have an example. A camera flash unit stores energy in a 150 microfarad capacitor at 200 volts. How much electrical energy can be stored? So first of all, you guys can start working on this, try it yourself, and then look for the answer. So what is a camera flash unit? You guys all familiar with this? If you're using the camera phone, the camera in your phone, it has the flash option that releases like a very strong burst of quick light, right? Or if you're using these fancy big cameras, DSLR, they come with external flash units. So the idea is it releases a lot of light in a very short period of time. So these kind of things, these kind of large outputs of energy in short period of time, it's difficult to achieve, difficult to obtain with regular batteries. Batteries are designed to release energy in a slow, constant pace. So we use capacitors. Capacitors can be designed to release energy in very short period of time. Or I told you, right, it's like a timing device, so you can adjust that time. You can have it like a fast output, you can get a slowly changing output. Either way, by changing the electrical circuit, basically the capacitor and the resistor combination determines how fast it's releasing its energy. So that's basically how the camera flash works. Okay, so let's see. So here we have, so basically what you have is a charge capacitor. And how do you charge it? Connect it to the battery. So here we have 150 microfarad capacitor. Connect to 200 volts. So you leave it some time, probably like a couple of seconds, and it's charged. Now you have this charge capacitor, 150 microfarads, charged to a voltage of 200 volts. When it is fully charged, it gets the same applied voltage. How much electric energy can be stored? Question is U, electric energy. It's a standard we use. Instead of E, we use U also as well for energy, because sometimes E gets confused with electric, so we use the term U for that. Okay. Straight away you can say U equals, think of one of those equations, We have half q squared over c, we have half qv, we have half cv squared. Here we haven't calculated q, so I'm gonna go with this half cv squared. So half times capacity times v squared, 200 squared. Now let's take the calculator and see what the answer is. So I get exactly 3. Now what's the unit? This is energy we are talking about, right? What's the unit of energy? We talk about different terms for energy. When it comes to electrical energy, we prefer to go with joules, so it's going to be just 3 joules. There's another unit for energy is Newton meters, but that is mostly for kinetic things. If something is moving, rotating, we prefer Newton meters. When it comes to electrical energy kind of stuff, we stay with joules. Okay, so the energy stored, this capacitor is 3 joules. Just to see the use of other equations, we can find the total charge stored in it, Q equals CV. So that will be 150 to the negative 6 times 200. So we have 150, 300, 2 zeros, 10 to the negative 6. Cancels out, 3 times 10 to the negative 2 coulombs. That's the charge. So if I want to use any of the other equations, for an example, energy equals half QV, at half times, I can use this 3 times 10 to the negative 2 multiplied by 200, cancels out, gives me 3 joules. It gives me the same answer. If I use the other equation, half q squared over c, I should get the same answer, right? So you can use any of the equations. Based on information you have, you can select which one to use. Alright, second question, part B, is talking about something new we haven't discussed before. What is the power output if nearly all the energy is released in 1 millisecond? Power output. What is the term power means? Now this capacitor has an energy of 3 joules. It's stored there. It's ready to be used. We can connect the capacitor to a light bulb, use it to produce some light. Let's say it's like a regular flashlight, so you want it to be on for certain time. So use it with certain resistors. You limit the current in the circuit. You put a bigger resistor, so it's going to decrease the current, so the light will be on for some time. In a camera flash, you want all that light to come out in a very short time, like a split second burst of light. So you use a small resistor, allowing a lot of current through it. So power means how fast you are using this energy. If you are using it rapidly, that means a lot of power. If you are using it in a slow pace, that means low power. So power output, power is defined as energy divided by time, or rate of energy. So power is energy, or energy usage, energy output, or energy produced divided by time interval. So we know that energy is measured in joules, time is seconds. So it's joules divided by seconds, so joules per second, also called watt, or W. That's the unit of power, joules per second, or watts. So power is associated in so many things, like for an example, vehicle engines, car engines, you say that a certain car has so many horsepower. Horsepower is also it's a historical unit. It's a British unit for power. There's a nice history behind it, how all these things came up. Here, mostly in physics and other sciences, we use the unit watts. Horsepower can be converted into watts. If you're buying, let's say you're going to go buy a light bulb or something, you look for 100 watts, 75 watts, 20 watt LED. That's the power output. The amount of energy it releases in a second, right? That's the idea of power. They talk about 1000 watt microwave oven, or like a hair dryer with 200 watts. So that's the amount of energy it consumes in a given second. So energy per time, right? Energy per second, that's power. So for this particular capacitor, if it's going to release all this energy in 1 millisecond, what's the power output? That's going to be energy divided by time, 3 joules divided by 1 millisecond. So that is 1 times 10 to the negative 3 seconds, that's milliseconds, gives us 3000, 3 divided by this, 3000 joules per second, or 3000 watts. Or we can say 3 kilowatts. Okay? Alright, that is energy storage. So we'll discuss few more examples in class and also through quizzes. So let's talk about an interesting conceptual situation. Let me clear this. Okay. So let's say you have a capacitor. You have an empty capacitor and you connect to a battery, you charge it. Now you have a charged capacitor. And then you're going to remove it from the battery. So the capacitor is charged, it has some charge Q. The capacity C. It has some charge Q, the capacity is C, the voltage across the plates is V, and it has some energy also stored in it. Let's say that is U. Now you have this isolated capacitor, the charge capacitor, a parallel plate capacitor. Now you're gonna make some modifications to this. Let's say you move the plates back and forth, you bring them a little closer, you try to pull them apart a little bit, you increase the length, the gap between the plates. What will happen to things that are stored in this capacitor? Right? So these are like interesting conceptual things to discuss. Let's look at an example. Capacitor plate separation increase. So the capacitor carries a charge Q, then disconnected from the battery. Two plates are initially separated by a distance d. Initially the separation was d. Suppose the plates are pulled apart until the separation is 2d. So we're gonna pull it apart and make it bigger. How has the energy stored in this capacitor changed? Will these things and this, will they change when you do this? That's the question. The question is asking what will happen to the energy. Is it going to remain the same? Is it going to be increase, decrease? Is it going to change? So how do we analyze a problem like this? So take a minute, think about it, and then listen to the video. So what will happen? Now the charges came from the battery. Even if you make physical changes to the capacitor, the amount of charge that was deposited on it won't change, right? In order for this Q to change, either new charges need to come to the capacitor or some of the charges has to leave the capacitor. As long as it's not connected to anything, none of this will happen. So Q will not change. So Q remains same. So what we are doing is we are moving the plates back and forth. We are actually pulling them apart. We are increasing the separation. What will happen to the voltage? We don't know. What will happen to the energy? We don't know. What about the capacitance? It changes. We know that capacitance is given by EA over D. So, if we increase D, if D gets bigger, capacitance decreases, right? When this increases, bigger the separation, this decreases. So if we increase D by 2, like if we make it twice bigger, the gap is now twice, capacitance will be dropped by 2. So now the capacitance is half of what it was before. If this was 100 microfarads, now the new capacitor will be 50 microfarads. Okay, so capacitance changes. Now let's think about energy. We know that this remains same, but this changes. Energy is given by if you think about the three equations, in this case, let's talk about this one. Half Q squared over C. So, what happens when you increase the plate separation? Capacitance drops, but charge remains the same. This term does not change. Q does not change. Oops, I made a mess over here. U is half Q squared over C. Q remains the same. This decreases by half. That means energy will be increased by 2. Energy will be doubled, right? Energy is going to go up. What else? So, summarizing everything, in this case, you increase the gap, the energy is going to go up. What about the voltage? This we can think in terms of Q equals CV equation. You increase the length, capacitance went down, this remains the same, no change. So if capacitance is going down, this needs to go up. So the voltage in the capacitor will increase. So there are so many ways you can think of this. You can even think about what happens to the electric field inside. It will be another interesting question. So think about these things. These are simple conceptual stuff. Okay? Alright, let's move on. Alright, so let's move on and applications of capacitors. That is something we will discuss a little bit during the lab as well. Let's see what other slides we have. Use of capacitors, heart defibrillators. We discussed this some time ago. We will talk a little bit more detail later down the line. Use electric discharge to jumpstart the heart and can save lives. I'm not so sure about this term jumpstart. Jumpstart sounds like the heart is stopped. What I think, I'm pretty sure about this, is it brings the rhythm, the right rhythm back. Fibrillation means heart is going out of rhythm. It's still beating, but not the right rhythm. So a sudden electric surge, the right amount of current and voltage can bring the rhythm back, can correct it. So that's the purpose of this device. And technicians, paramedics, doctors, they first check to see whether the person needs the defibrillation. It depends on what is going on with the heart. If the heart is not pumping, if it's stopped, I think they don't do this. They do something else to bring it back. But if it is out of rhythm, then you can use this electric shock. And the automated ones you see around, actually these things they have a little microchip. This is a little computer inside. It first detects the heartbeat to see whether the person needs this defibrillation shock, and then only the machine functions. So anyways, this is a good application. And also another thing, lot of electrical devices like refrigerators, washing machines, microwave ovens, they have capacitors inside. These things, this is like a talking about some electrical safety tips. Some of these capacitors are quite big, and even if you unplug the device, the capacitor can retain charge inside. So let's say something wrong with the machine and you decide to open the cover and take a look at it inside. You have to be really careful. Even though it's unplugged, the capacitor can contain a considerable amount of charge, and without knowingly, if you touch the capacitor area or some conductors, you can very well get an electric shock. Could get a very bad electric shock. So if you are not familiar with electrical repairs, don't do it. Get somebody who knows the subject to do it. Just keep in mind, unplugging something doesn't mean it's completely discharged. Especially like I think of straight away, but big electrical equipments can have big capacitors inside. Okay. All right. Let's move on. All right. So the next thing I want to discuss is that the dielectric medium. If you remember that capacitor equation, so let's clear this. The parallel plate capacitor, and to find the capacity we use this equation, naught over d, plate area, the plate separation, and the permittivity of space, free space. This is 8.85 10 to the negative 12. Now this negative 12, if there's nothing between the two plates, we say that that's an air gap. If you have an air gap, that's the number goes in. But most of the practical capacitors, we fill the gap with something, with some insulating medium in between. This is called the dielectric material or medium. This has several advantages. I mean, this is an insulating medium. It's not a conductor. It opposes the electric current going through it. Increase the resistance, if you say. This has other advantages. So the main advantage is increase capacitance. Then strengthen the capacitor. So structurally it's stronger, right? So it's a stronger capacitor, structure wise. Structurally it's stronger. And you can make the capacitor really small also. You can bring the two plates really close, still they won't touch each other because there's something in between. So make it smaller, right? So make it physically smaller. So you can put more capacitors in a given space. So there's so many advantages like this. So what are the examples of dielectric stuff? A lot of insulators like glass, plastic, wax. So I'll show you a list of insulators that are commonly used. So all these things can be used as dielectric medium. So let's go to the next slide and see what we have. So when you put something in between, let's say you put, for an example, decide to put some wax kind of material, candle wax kind of thing. This number changes. So the new permittivity is given by something called the dielectric constant K, which is K. And then, so wax will have some K number, plastic will have a different K number, different oxides will have their own K numbers. So the equation changes. E equals K times epsilon times A over D. All you have to do is find the K number from a table and multiply it with the permittivity of air. So let's look at some examples. So look for the middle column. Vacuum and air has the K number of 1. So that means our original equation, right? Epsilon is being multiplied by 1 means still the same number. Paraffin 2.2, polystyrene 2.6, vinyl 2 to 4, paper, so and so. You see different numbers. Go to strontium titanate, very high number, 300. So what's the advantage? So let's say we have a capacitor, for an example. We have a parallel plate capacitor with D equals 0.1 millimeter, a small, okay, let's say 1 millimeter, and plate area is, let's say, 5 centimeters squared. And if it is an air gap, what's the capacitance? So capacitance is EA over D, 8.85 times 5 times 10 to the 5 centimeters squared. So I'm going to make it meter squared, dividing it by 100 twice, -4. 1 millimeter, 1 times 10 to the -3. So do the math. To 1. Huh. Since I don't have the calculator, I'm going to make it 10. Easier. Gives me 8.85. What am I? Oh, 10 to the. I'm sorry, guys. Missing 10 to the -12 here. 10 to the -12 farads, or 8.85 picofarads. Now, I'm going to use a dielectric material. Let's say we put, what do we put? Glass, a piece of glass, a thin layer of glass, a 1 millimeter thickness layer of glass in between. Okay, let me draw a new diagram for this. Then I'm going to modify the capacitor. So here's the capacitor, everything else same, but I'm going to put glass in between. So the new capacitance, K times EA over D. K is dielectric constant for glass is, from the list, from the table I can see it's 5. So 5 times 8.85, 10 to the -12, 10 times 10 to the -4 over 1 times 10 to the -3. So everything else same, the capacitance get multiplied by 5 times. So it will be 5 times 8.85, something close to 45 approximately picofarads, maybe 44. So that's the advantage of using a dielectric constant. In the table next to that, you see the next column, dielectric strength. That is like the max voltage it can handle. Like you can put something in between and you can apply a huge voltage. Sometimes these things can break, means these things can short circuit. It's not that, you can apply like thousands of voltage all the time. There's limitation. So that's why that's what this next column says, the dielectric strength. Divide not need to go there. If you have to, I'll talk about it. So with that, let me see whether we have anything else we need to discuss real quick. So with that, we come to the end of the discussion of capacitors. So here's a brief summary of what we discussed. Capacitance given by this equation: parallel plate capacitors, capacity equals epsilon times A over D. Capacitors in parallel, you just add the numbers. Capacitors in series, you add them as reciprocals, 1 over. Dielectric is an insulator. For a parallel plate capacitor, again, you multiply the capacity by the dielectric constant, you get the new capacitance. Alright, so with that, we can conclude capacitors, and thanks everyone.